So activity 2 is all about learning about space-time and how it affects the paths of light, and then later on you'll draw space-time diagrams, or x versus t, position versus time, and think about how you can interact with, people can interact with things in their present, past, and future, and what things they can't interact with. And so this first diagram, or first main demo, is where you construct this model for space-time curvature, where you get something that can stick up pretty high and narrow to create this sort of curve with a very stretchy sheet. And it's probably best if you tape it down ahead of time, but you can already notice that we've had to add a little bit extra because it's quite stretchy. And so this first demo is really just to demonstrate the bending of light in different levels of curvature. And so this first piece of tape, the idea is that you want to take a piece of tape, masking tape works best because, or this type of tape works best because it's not very sticky, and you don't want it to be too sticky. And the idea is to pick a point, the idea would be an object that emits light, and so draw different rays as it comes off of the light. And the idea would be the emitting object is here, you have something that has a lot of mass and gravity in the middle, and then the Earth or some observer is on that side. And so the idea is that even if light might go directly towards the observer, it might change. And so if you take a piece of tape and just go straight forward, of course, making sure it lays flat, it will eventually directly hit the black hole and stop, right? Because the black hole captures the light. Another version of the ray is if the object emits it slightly offset from the black hole. The idea is you want to lay the tape down as flat as possible on the surface, and to make sure there's no bends in the tape. And what will happen is it will bend naturally in the curvature. And so even though it goes sort of, the initial ray of light points this way, the curvature curves the ray of light, so now it points that way. So an observer, so if the Earth was here and you saw this light, you would say the object that emitted it lived over there. Right? So this is bending light. And you can also see that if you took a different trajectory, it wouldn't really bend much at all. So on a flatter piece of curvature, if you have a different angle and make sure the tape lays flat on the surface, it bends a little bit, but not quite as much. And so if you're back at Earth, there's a very slight bend, but it's closer to the actual source. And so the idea here is the students would run through this experiment, and then they would draw it, a diagram, essentially looking at this from above, and talk about the different levels of curvature.
Do you need my put a little translation?
If you want, well, I mean, if you guys want.
Okay.
I don't know if you have questions or comments, or.
Let me brief translate.
Oh, yeah.
所以这个道具呢，它其实这个是一个漏斗，它就是一个凸起来的东西，就是你们可以用烧杯都可以。那它基本上就是跟那边的不一样，它就是用一个 upward 的方式，因为它这样子就可以开比较牛顿的重力的影响，就不会陷入刚才那种迷失。那这个布这样子做好之后呢，这边是所谓的光源，就是你的星体它放出来的光，这边是地球，就是你观测光的地方。那基本上你就是放这个胶带，等于就是去感受这个曲率。那其实你们都可以等一下拿胶带试试看。那其实我们昨天在前阵子在试验这个东西的时候呢，我们其实是有点因为我们知道它会弯嘛，然后其实我们在放的时候，我们就很想要弯它。就是我觉得要放这个胶带要弯它，它其实不用，你就是胶带平铺，对，平铺就可以，它自然你就会看到这个是弯的。 你们如果说这个角度看不清楚的话，你们可以试着
所以如果现在把中间拿掉，我们看到会是弯的吗？
直的。
你照着它的平面贴的时候会变直的。
对，但是它虽然会有皱褶啊，因为你现在是比较长。对对对。就是你们可以站高一点看的话，你会发现这个弯的还蛮明显的。就是说你们从上面往下看的话，对，对，但我只是沿着这个布的这个表面这样子轻轻的并铺下去而已，我并没有刻意的让它转弯，或者是找一个特定的方向。那如果说你觉得你的贴出来的线它弯的不够明显的话，那就代表说你中间这个不够高挺。对，你如果垫高一点，让它落差大一点，然后这个路径靠近一点的话，它其实就还蛮明显的。对。
So you can see how the light ray is supposed to go this way,
走直线。
but now it comes straight this way.
有没有可能贴出一条是这样到这边，就是正好对面？
可以，
可以
有机会，
但是要很小心的。
应该说你要找对角度。
找对角度。
找对角度。
There's an angle that you can pick that would take you exactly from here to here.
但这是因为是弹性布，所以你贴的时候难免会压到。
就是说，因为这弹性布是为了建构这个曲面出来的。对，那基本上你在贴的时候，其实就是轻轻的，然后沿着这个表面，但你就不会人为的带入太多你的。像我一开始我就是想要它转弯，然后反而就带入了太多，但是后来发现它其实不要，它只是要让你看到这个。
顺着它。
对对对，顺着它，你就会看到它会转的。
就是有没有要求上面不可以有凸起，或者是？
对，希望它尽量是平的，不要凸起。那另外再跟大家分享一个我们的错误示范是说，这个布是长方形的，其实应该正方形的会更好。对，因为它这样子有一点，对，应该是正方形的会更好。对，对对对，所以这个是我们的错误示范。
正好是不是圆形的会更好？
圆形的
也是可以。
对，但是因为是教材就是以方便为主，对，所以它是
越靠近这个
就是偏折，
对，
就看起来偏越多这样。
所以有点像那个 slingshot， 重力弹弓。
那这个模型没办法显示出那个 event horizon。
How to show the event horizon based on this model？
There's not enough curvature.
曲力不够，因为event horizon是要光线不能逃出去，所以你其实要一个，你可以用想象的，就是这个如果一直往上到达一个起点的话，那你如果说你有条胶带，当你拉那么高，然后有条胶带靠近它的时候，你会发现，其实可以想象，它其实你要绕过去，它就开始自己转，它会沿着那个上去，对不对？对不对？
Well, yeah. So I think actually you could model a black hole if you had a straight cylinder.
Yes.
And then you could wrap it around the cylinder. So if you had a paper towel roll to put on top.
Or a cone, paper cone or something, like an ice cream cone.
Well, a cone would still have curvature.
Oh, right.
I'm talking about it has to be fully straight.
Yeah, okay. Yes.
And so you could use like a cardboard tube or something. Like a can.
Yes.
就是卷筒
注重在那个保鲜膜的注重中间那一根，
那个粗钢纸巾那种看起来高一点。
对，因为你到靠近起一点内部的话，它那个 potential 就已经是完全非常的陡，非常的陡。
This is a black hole, right? Because the tape always goes in the same place. It doesn't curve out. Is that
yes. Okay. 对啊，如果说你们准备一个改进这个展示，你们做哪一根对的话，那也许他们学生就会发现说，哎，贴胶带贴到某个靠近足够距离的话，它开始就自己缠到了一下，那就是掉进黑洞的意思。对。
对，如果继续到的话，它就会。
对，可以想象出来啊。对。
不要很大。
对。
这个模型可以避免那个网箱跟那个表动力学的那个症结吗？
对啊，因为这个就是它故意往上啊，因为说你这边没有一个东西是把布往下拉，是靠重力，因为你这个曲率就是决定于你的里面这个高度多大，而不是你挂的东西。那基本上，而且也没有，你这个展示里面没有需要滚动的珠珠的概念，你不需要重力去导引这个珠珠在上面进行一个轨迹，你完全就是
They were talking about how this system
那如果
avoided
要跟
Newtonian
学生或学习者
force
解释位景的时候，
effects.
你就要把那个位景的那个正负号
This difference
减
is
少过来
that.，
你就对啊，就是一个镜像而已，对。
因为他们现在受到太多那种螺旋存钱筒的影响，
对，
都一直以为一定要像是一个。
对，其实我们这些人在准备看这个教材的时候，一开始也是觉得有点难接受，就是说他为什么要刻意的制作这个教具是要倒过来的。那后来经过仔细看，然后自己尝试之后才知道说，其实它也是有它的道理，就是它为了避免跟牛顿力学造成不一样这样。对。
Okay, so go ahead.
Light cone.
Yeah, light cones. Okay. So the next part is all about, like I said, space-time diagrams. So space-time, or just space-time, all one word. And so the idea is you need to talk about, instead of the two-dimensional, just space part, which is the first activity, now we have to include time. So we have time and space, or position, right? So the space, time. And so I think the first part is talking about how to draw velocities or speeds, although actually it really is velocity in this case, because it's a vector. And so velocity, remember, is change in position, change in time, right? So that means if you change in position, you change in time, so velocity is going to be a diagonal line in this space, right? And so if you want to put units on this, so let's say this is 1 second, and this is 1 meter, then something going 1 meter per 1 second would be exactly a 45-degree angle, right? So this is E equals 1 meter in 1 second. Now when we talk about relativity, we like to think about the speed of light, of course, and so the speed of light is much, much, much larger. And so if we use the same units, the speed of light would be essentially horizontal, right? It would go all the way out there, which is inconvenient. And so we want to change the units on the diagram to be able to show speed of light better. And so what we can do is we can just change the units of time so that they're in units of speed of light. So we just multiply by c. And so now for a particle, so a photon, to travel 1 second, it will travel 300,000 kilometers. And so because these are now in the same unit, the speed of light is now also 45 degrees. So, right. And this is just talking about the first question. And then you can ask, the next part of the question is about how to draw velocities that are slower than the speed of light and faster than the speed of light. And so if a velocity is slower than the speed of light, it would live over here, be less than c, and this velocity be greater than c, right? And so of course only one of these is allowed. You can only do this because the speed of light is the fastest thing. You can't go faster than the speed of light. It's the speed limit of the universe. And so we're not allowed to do these. And this is where the light cone comes from. So let's draw another diagram. T X. And let's draw a person. Right? And let's think about what are all the possible futures that this person has, right? So this person can only travel at the speed of light, and he can travel forward, or he can walk forward, which is increasing his x position, and he can walk backwards, which is decreasing his x position. And of course, he's always moving forward in time. But he could also stand still and not move at all, right? So if he's standing still, his trajectory just goes straight up. If he moves forward, his trajectory looks like this. And if he moves backwards, his trajectory looks like this. And so I see some confused faces maybe. Do you have questions or clarification? Maybe?
这边要介绍那个时空图跟光锥概念，因为这个 demo 这个教具只有展示空间区，那实际上你如果要讨论孔腔的话，你必须把时间加进来，所以他们就是有一个简化的，就是时空图，就是你画上位置跟时间这样。那基本上它这一部分在解释说，你如果一个光在上面的话，要怎么画？因为光速太快了，所以我们第一个就是先改单位，把时间乘上 c， 那这样子的话，光速在你这个图上面的话，它就是会一个斜率为1的直线。那小于光速就是会你的线就偏过来这边，那大于光速线你的这个线就会偏到这里。这是时空图上的概念。那这边就是要开始介绍光锥，因为时间永远是往前的嘛，不管你的物体的运动状态是怎么样。但是物体的运动状态它可以假设因为这个是一个维度的，所以它可以正的可以负的，所以它有两个方向，所以光锥的概念就是说，某一个时间点、某一个时空点上面，那个它可能拥有的可能性的未来。那它如果光锥是这样子的，所以它有一个可能性的过去跟可能性的未来。那如果在这个光锥之外的，就跟你没关系了，因为它根据爱因斯坦相对论，根据光速是最快的，而且是定值的这个理论，其他的东西就跟你没有因果关系。Okay, great.
Yeah, and so this just describes the directions this person can go, because he can only move forward in time. And so the fastest he could ever move forward in time is at the speed of light. So this is E equals c, or this is E equals minus c, and this is of course E equals 0. And so this cone, or cone of possible directions he can go, is this person's entire future. He can only go places and do things inside of this cone, right? So if he had a friend that lived over here, let's say this is Alice and this is Bob. If Alice has a friend that lives over here, well, he can never meet Bob, or Alice can never meet Bob, because he would have to travel faster than the speed of light to talk to her, or him. So, 5 minutes on that? Yeah. Okay. So this is mostly the idea of what this section is talking about. I think a lot of this is sort of explanatory in the questions. It kind of walks the students through how to think about space-time diagrams. I think maybe the trickiest part is the third exercise, which is all about what happens when there's a gravitational object in the same space-time as another person. So let's say there's a black hole here that has a lot of gravity. Well, we said the black hole changes the curvature, and so what will happen is it will change the light cone. So depending on where the person lives, their light cone will get tilted towards the black hole, right? And so what we call the event horizon, so here's the black hole. What we call the event horizon is the point where the person's light cone tilts 90 degrees. So this person can travel the speed of light in one direction, but he can't travel faster than the speed of light, so he will never be able to go to this side of the universe. He's trapped in this side. And of course, if he travels slower than the speed of light, he will hit the center of the black hole. And, well, he's already disappeared forever for us, but you know, if he stays at the event horizon, he can live for eternity. But if he travels slower than the speed of light, he will have a finite history. And so the idea is that, so this person on the event horizon is sort of locked in place. A person over here, their cone is tilted, but not by quite as much. And of course, the person inside, their cone is even worse. And so their future is always finite. One way to think about the event horizon is, and in fact explicitly, if you do the math, what happens is one of your spatial directions turns into time. And so if you think about, okay, going forward is increasing my x position. As you cross the event horizon, increasing your x position now means increasing your time. And so you swap one of your directions with the time direction. And so that's sort of, it's kind of confusing, not on purpose, but it just happens to be so. And of course, this is what makes some of relativity sort of a little bit complicated, is that it really does change how the universe works. And so that's the last part. And then there's a final thing that sort of collects everything together, that answers questions about light bending and space-time diagrams. But I think if they're able to solve, you know, if they're able to do well in the first demo and they're able to get through the space-time diagrams, I think the last section should be very straightforward.
所以这个就是刚才讲光锥嘛，那后面第二部分就是把重力的物体放进来。它其实它这边没有很明确的推导，但是它就是告诉你说，当你有重力的话，你这个光锥本来没有重力的话，光锥的话都是45度角、45度角这样子，这个是有点像是小一相对论。但你有重力放进来的话，这个光锥就会往你的重力的来源倾倒。这个是就是说概念上是正确的，但是中间详细的推导那个就需要再去想，就是说不在这边讨论这样子。那当你如果说你这个黑洞，当你靠近这个黑洞的话，就是有一个东西它靠近黑洞，它就受重力影响，它光锥就越来越歪，越来越歪，直到你到世界的时候，它正好就整个倒下去了，变成转90度。这个时候变成你的就是它可能的未来呢，本来这个光锥上出去，它都是它可能的未来。现在因为这样倒下来，变成它可能未来都掉到世界里面，就是它的未来全部在黑洞里面，所以它就等于跟外面的世界就断开。这就是为什么世界它这个黑洞外面这一圈东西就是一个 horizon， 就是一个目前一个障壁在那边的原因。当你这个光锥打下去的时候，它的时间轴跟你的位置轴也正好交换，所以这边说像刚才不讲，就是你如果叫世界的话，它的本来你以为是在位置上行走，但是你可能现在就变成你的时间就不知道怎么讲，就是有点 tricky， 就是你就变成说你本来你可能就简单这样讲，就是你可能在同一个时间出现在无限多个地方，在这件事情里面。如果说照这样解释的话，对啊，它就是变成一个奇怪的事情。对，但就是这个 教案就是希望说，可以透过这些简单的集合跟概念去介绍广义相对论给学生。那其实我之前在读广义相对论的时候，其实有看过一些原文书、外国原文书，它也是用类似的方式去介绍，它没有很多数学的式子，完全是用这种图解的方式，其实是还蛮 OK 的，就是中学生其实是可以理解的，就是说已经有这种专门制作给中学生的广义相对论的用书，有在市面上这样，对，其实也有做给 baby 的，你有看过那种小婴儿读的量子力学，小婴儿读的相对论，就是你们去Amazon上去可以搜寻得到这种书，虽然说到底看不看得懂，还是说它只是一个趣味，我就不是很确定，对，但是基本上这是一个方式这样，对。
吴老师请教一下，那个一个时间出现在不同的位置，或者是时间跟位置的交换，能解释那个趋速旅行吗？或者是平行时空吗？因为学生可能会这样问，就是他们很直觉就觉得说一个时间出现在不同的位置，或者是时间轴跟位置轴交换，他们不禁联想到那个
你
不好意思，我们
我可以再补充一下，就是不行，简单答案不行。可是刚刚对于光锥，其实我们可以有另外一个想法。我们刚刚说光锥在离黑洞很远的地方是往未来讲嘛，可是到里面后来不是那边变这样。可是其实它物理上的意义是说，我们离黑洞很远的地方，我们说广义相对论考虑时间跟空间，所以我们有3维的时空，前后左右上下。可是我们加上时间之后，时间跟空间一并考虑之后，时间的确是有个特性跟空间不一样。大家可以想象的是什么？
时间一直在走。
对，它只能往前，不能往后。所以当我们到黑洞以边红蓝之内，我们什么东西只能继续减少，不能增加。我们只能在一个方向上，这就是距离。我们距离往黑洞整个热体的距离只能单一方向的改变，这就是它的物理意义，对吗？在很远的地方，我们没有办法选择，只能让它持续的变化的是时间。可是到以边红蓝以内，我们没有办法选择，只能让它持续不断变化，一直缩小我的跟这个热体的距离的，就变成空间。所以它的光锥打过来，是这个意思，物理上的意思。然后刚刚讲的曲率引擎啊，它需要改变在时空周围附近的几何，所以它讲的几何是变成说，整个几何是我们像是一个粘土一样，我们可以去捏造，那我们可以去捏造一个我们想要的几何。曲率引擎是说，我们可以让它的局部，没有违反广义相对论，也没有违反狭义相对论，但是从远方来看，我会觉得这个太空船它怎么可以超光速来运动，是因为它改变它的局部的时空几何，所以它跟黑洞要用的时空几何不一样，可是它有点像是很简单的说，有点像是它在太空船前面摆黑洞的几何，在它后面摆一个白洞的几何，所以它一直推着这个时空这个太空梭在跑，可以看起来远方看起来它是真的超光速在运动。
曲速泡泡，
曲速泡泡
就是你们在聊曲速引擎嘛，就是 Star Trek 的那个东西嘛。那我知道是 Star Trek 那个语，但就是超光速引擎的话，就是你光速在时空的结构中是只能用光速前进，但是它没有爱因斯坦相对论并没有限制这个时空结构本身它怎么样可以运动，也就是说它可以迅速的捏紧或者是迅速的拉长。所以你如果说你在我们的时空结构中产生一个泡泡，然后它这个泡泡是可以在时空结构中以超光速前进。那你放一个太空船在那个泡泡里面，它相对于那个泡泡是没有违反相对论，但是整个泡泡本身是可以超光速前进，类似这样的概念。但是那个能量太大，所以做不出来。
就我再补充一下，就是我们今天讲到很多几何的时空，但是相对论的主要概念是说，我们可以用几何的方式去理解时空。那我们的附加好处就是重力原来其实就是弯曲时空的展现。那时空它到底有什么限制呢？它就是等效原理，就是任何一个地方 局部上，我们只要恢复到自由落体，它局部就是平坦。但是很多一小块一小块的平坦，可以组成一个大尺度上看起来是弯曲的状态。譬如说我们在舞厅看的玻璃球，它是每一个小面都是平坦。所以爱因斯坦他允许的时空概念像是这个样子，他不会允许，比如说某个地方尖起这种时空。那到底有哪些可能的时空的结构？那黑洞是一个，刚刚说曲率引擎是一个，摆动是一个，它只是把黑洞的时间反转。那时空到底还有哪些特性？我刚刚说的旋转时空又是另外一个。宇宙早期的时候，时空被长出来，那在时空里面的两个星系被推的，它们彼此远离的速度可以超过光速，这也不违反广义相对论。那但是拉回天文的角度，这么多可能的广义相对论的解里面，哪些是真实存在在宇宙中的？目前为止只有黑洞。所以，比如说我们有白洞的解，我们有曲率泡泡的解，我们有虫洞的解。目前天文学里面没有看到非得用这些时空结构来解释的天体。所以从这个角度看，黑洞是为什么天文学家那么感兴趣？是因为我们真的看到，我们觉得这个就是黑洞。那其实我们今天就一整个下来回头想，这样子的时空结构真的存在，是很奇怪的事情。它是真的挑战我们对重力最基本的认识。好，补充到这边。
Oh, well, I don't know how much time we have left. Probably none. We're already over, I think, a couple hours. But there's one more activity that we included. It's related to, the telescope and resolution. And there's the second part of it is related to photon momentum and how you can use. Oops.
Sorry.
It's okay. The brightness of photons to determine direction of movement. And I since we don't have a lot of time, I guess I'll maybe just talk about the difficult parts of this activity, which is the flashlight part and the diffraction. So, yeah, one of the activities requires that you use a flashlight with a circle in the middle. So you create a ring of light, and then you're supposed to use the pencils with the rubber band and make a small slit and look at the light through the slit. And the idea is that at the narrow part, you experience diffraction, which is changes in the light because you don't have enough space to see all of the light coming from the object. But as you move towards the top of the pencils, you open up your aperture or your telescope, and now you can see all of the object, and it looks it looks undistorted. The problem with this experiment is that if you have bad eyesight or an old prescription like I do, it doesn't really work very well. Essentially, anywhere you look at it, it looks slightly distorted. And so if you have perfect eyesight, maybe this experiment works better. But I think we found... okay. Well, you have good eyes. So it depends on perhaps the student, right? And so it might be a little bit more challenging. But actually, let's just set this here. But otherwise, I think the other activities in this section are actually pretty useful. There's one where you draw a tiny circle on a card. So this is activity 6, number 1. So the idea would be, I can draw a very tiny circle. So here I've drawn a dot and a circle, and when you're up close, you can see both the dot and the circle. But if I was in the corner of the room over there, I'm too far away, and it would just look like a single object, right? But the demo has you draw a tiny circle with a pencil and a piece of paper, and then look at it in your hand and then across the room. The idea there being that resolution is dependent on distance and the size of your aperture lens. And so then there's a couple of exercises that is really just algebra and math and unit conversions that determines where you go through different exercises that figure out diameters and resolution. And I think that's relatively self-explanatory. It gives you the equation you need, both the equations you need, and it's just rearranging terms in the equations to get the appropriate answers. And then I think yeah. And then the last part is again about photon direction and momentum. And again, I think it's pretty explanatory in the document, but you essentially just write, draw rays of photons coming off of a ball. And then depending on if the ball is stationary or if the ball is moving, the direction of the rays will shift. And that's how you can sort of explain why one side might be brighter than the other. If you look at an object from one side and it's moving away from you, more rays are going away from you than towards you, and so it looks dimmer. Whereas if an object is moving towards you, more of its rays are sort of directed into your line of sight, and then it appears brighter. This is why the black hole for M87 is dim on the top and bright on the bottom, is because the material that emits light is traveling towards us on the bottom, and so it beams, the word we use is beaming, it beams the light towards us, and so it's brighter, and it's moving away from us in the top, and so it's beaming its intensity away from us. The actual details of how this works can get a little complicated, and relativistic beaming requires some pretty advanced algebra, but depending on the level of your students, you may want to try that at a later point. It certainly doesn't require calculus, but it can be some pretty tricky math. I don't know, maybe Hung-Yi has probably taught special relativity at some point. He can describe what might be necessary.
对啊，这个刚才在讲的是 Activity 6。那我们因为时间的关系，我们没办法太深入的去看。那刚才 Brett 就是跟我们讲说，他其中的那个操作 Activity 6是关于 M87黑洞的观测，就是有一些相关的演练。那这个 Activity 6我们试过，它如果它是用那个2支笔去模拟你的那个孔径的大小。当然好像是说眼睛好的人看得出来，像我们眼睛不好的都看不出来。所以这是一个提醒，就是说，也许你们会看到，对，会发现说跟他讲预期的不一样的地方。那后面的话，后面的几个 part 就是说就是有一些计算，但是它都是相当自导式，就是你根据它的导引，其实是它会慢慢告诉你解释，这样就是就好像自导式步伐，就是自己导引自己的这种一个过程。它最后一个部分是在讲杜普勒冰影就是黑洞的杜普勒效应。那它就是在解释为什么我看到黑洞影像有一些部位会比较亮，有一些部位比较暗，那是因为杜普勒效应的关系。对，大致上是这样。
那我们因为我们今天差不多活动了解，我们不想耽误大家太多时间。对，那我们想要请问一下，说这是我们第一次举办这个有关黑洞的教室。那如果下次再举办类似活动，你会想要听哪一种主题的呢？有特别想要的主题吗？
你要列举一下，有恒星，
有恒星、系外行星，还有宇宙膨胀，
外星生命。
没有。